Welcome back, everyone. If you've been watching AI lately, the model's writing code, making incredible images, understanding complex data, you're seeing deep learning in action. We're talking models hundreds, maybe thousands of layers deep.
Yeah, and it's funny because for decades, that very depth, the thing that makes them powerful, it was the barrier. It seemed impossible.
It's a real paradox, isn't it? You need depth for the model to learn those complex hierarchical things, breaking down big ideas.
Absolutely mandatory. But making a network deeper used to make training just fall apart. Instantly fragile, often catastrophically so.
So that's what we're diving into today. We want to unpack that problem, the gradient flow crisis, as we're calling it.
Right, what exactly was stopping deep networks from working?
And then crucially explore the ingenious fixes, the mix of architectural changes and clever algorithms that really unlock this whole modern deep learning era.
It's like mapping the breakthroughs that gave AI its current superpower, learning deeply.
Okay, so to get the solutions, we first need to really understand the problem, or problems. You mentioned gradient instability.
Exactly. There were two main failure modes stopping learning in its tracks: vanishing gradients and exploding gradients. The twin crises, really.
Let's tackle vanishing first. That sounds subtle, like it creeps up on you.
It is. It's the silent killer of training. So training uses backpropagation, right? Sending that error signal, the gradient, back through the network layer by layer.
Using the chain rule from calculus.
Precisely. And the chain rule means multiplication. Lots and lots of multiplications.
Okay.
If you have, say, 100 layers, that signal gets multiplied 100 times on its way back.
Okay. And if those numbers you're multiplying by are small?
That's the killer.
Hmm.
If the multiplier specifically, the derivatives of the activation functions in each layer are consistently less than 1, the signal strength just decays exponentially. Think trying to whisper a message down a super long line of people.
By the end, the message is just gone, or totally arbled.
Exactly. The layers closest to the input, the ones that need to learn the basic building blocks, they get almost no signal. So they learn incredibly slowly, or sometimes just not at all.
So the network isn't really learning deeply then?
Not effectively. The deeper you made the network, the worse the vanishing gradient problem got. It was a fundamental roadblock.
Okay, so that's the signal fading out. What about the opposite? Exploding gradients sound loud and painful.
They are. It's the inverse problem. Same chain rule, same multiplications, but now imagine the multipliers are consistently greater than 1.
So the signal gets amplified each step.
Wildly amplified. It grows exponentially huge. Instead of a whisper, you've got a sonic boom echoing back.
What does that do to the training?
Chaos. The weight updates become enormous, totally unstable. The parameters just jump erratically. Your loss function, it goes haywire, oscillating wildly, or just shooting off towards infinity.
And that's where you see those nan errors pop up, not a number.
That's often the end result. Numerical overflow. The calculations break down, loss becomes nan, and your training run just crashes, completely stops.
Wow. Okay, so you're stuck between the signal dying out or blowing up. A really narrow path.
A very narrow path, which is why the first fixes weren't about fancy architectures yet. They had to focus on just making the basic building blocks more stable, improving the components.
Right, shoring up the foundations first. What was the biggest change there?
Hands down, the biggest component breakthrough was changing the activation function, moving away from things like Sigmoid and Tanh, which, squash the output into a small range.
Why was that squash problematic?
Because in the squashed regions, the flat parts of the curve, the derivative is tiny, close to 0. That directly caused the vanishing gradient problem.
So what replaced them?
The game changer was the rectified linear unit, ReLU.
Ah, ReLU. It seems so simple, just max 0x. Why was that such a big deal?
Because of its derivative. For any positive input, the derivative of ReLU is exactly 1.
So no shrinking multiplier.
Exactly. The gradient just passes straight through, unchanged for all the active neurons. It doesn't decay in those positive regions. This one simple function suddenly made it possible to train much, much deeper networks than before.
But ReLU wasn't perfect, right?
Yeah.
There was the dying ReLU issue, where neurons could just get stuck outputting 0.
That's true. If a neuron's weights got adjusted, so its input was always negative, it would always output 0, and the gradient flowing through it would also always be 0. So it stopped learning entirely. It died.
Which led to newer functions we see now, like GELU or Swish, especially in big models like transformers.
Right. It's about refinement. GELU, that's Gaussian error linear unit, and Swish offer smoother activation curves. They don't have that hard 0 cutoff like ReLU.
Smoother means better gradients.
Yeah, they provide a non-zero gradient almost everywhere, which helps avoid the dying neuron problem. And GELU is adaptive. Its shape changes slightly based on the input statistics. It turns out this leads to, well, more stable training and slightly better performance, especially in those really large, complex models. That's why they're standard in transformers now.
Okay, activation functions make sense. What was the next foundational fix? You mentioned starting things off right.
Strategic weight initialization. You can't just throw random numbers in anymore, not with deep networks.
Why not?
Because if your initial weights are too big, you risk exploding gradients right from the start. Too small, and you vanish before you even begin.
So initialization is about finding that Goldilocks zone.
Pretty much.
Yeah.
The goal is to set the initial weights so that the variance, the statistical spread of the signals, stays roughly constant as information flows forward through the network, and critically, the variance of the gradients stays constant as they flow backward.
I've heard of Xavier or Glorot initialization and then he initialization. What's the difference there?
Xavier was designed mostly for the older Sigmoid Tanh networks. Heat initialization came later and was specifically designed for ReLU.
How does it account for ReLU?
Well, ReLU sets all negative inputs to zero, right? That effectively cuts the variance coming out of the layer in half compared to an activation that doesn't zero things out. So heat initialization compensates by essentially making the initial weights a bit larger specifically, scaling the variance based on the number of input neurons to counteract that effect. It keeps the signal strength stable despite ReLU's behavior.
Clever. It's like statistical pre-tuning.
Exactly, setting the stage properly.
Okay, activations, initialization. What about tackling the explosions directly, the loud crashes?
For that, we have a more direct intervention, gradient clipping. It's like an emergency brake.
How does it work?
If the overall size or magnitude of the gradient vector suddenly gets too large during an update step.
Which would cause that chaotic jump in weights.
Right. Clipping just says, whoa, that step is too big. It calculates the total magnitude, usually the L2 norm, of the entire gradient vector across all parameters. If that magnitude exceeds some predefined threshold,
You just cut it off.
not quite cut it off, you rescale it. You shrink the entire vector down proportionally so that its magnitude exactly matches the threshold.
Ah, so you keep the direction the same, the direction the network wants to learn.
Precisely. You preserve the learning direction, which is crucial. You just limit the size of the step you take in that direction, preventing it from becoming so large that it destabilizes everything and gives you those nans.
Okay, these feel like essential patches. Better parts, better starting point, emergency brake.
Yeah.
But you hinted these weren't enough to get us to truly deep networks, hundreds of layers deep.
They helped immensely, but yeah, to really break the depth barrier, we needed a fundamental change in the architecture, something that changed how information flowed.
And that's where skip connections come in. I like thinking of them as gradient highways.
That's a perfect analogy, because that's exactly what they provide, an express lane for the gradient. The breakthrough idea here was residual learning, pioneered in ResNets.
Before ResNets, just stacking more layers, even with ReLU and good initialization, could actually make performance worse, right? The degradation problem.
Yeah, counterintuitively, adding layers could hurt. The thinking was, it's actually really hard for a stack of layers to learn an identity mapping.
Meaning just passing the input through unchanged.
Exactly. If the optimal thing for a block of layers to do was just let the information pass through, the network still had to struggle to learn to make all its weights effectively zero out the transformation. That's hard.
So how did skip connections fix this?
By changing what the layers learn, instead of forcing a block to learn the direct transformation, say HX.
The skip connection takes the input X and adds it back after the block.
Right, so the block only needs to learn the residual, FX.
Right.
The final output is HX, FX plus X. Now, if the optimal thing is the identity mapping,
The block just needs to learn to output 0. Fx equals 0.
which is much, much easier for the network to do, just drive the weights towards 0. This identity mapping capability instantly solved that degradation problem.
Okay, that's clever. And the gradient highway part, how does that help the gradient flow?
That addition, the plus X part, creates a direct, uninterrupted path. When the gradient flows backward during backpropagation, it hits that addition point.
Oh.
Part of the gradient flows back through the residual block, Fx, but another part flows directly back through that identity connection X. The derivative through that identity path is just 1.
Ah, so it bypasses the potentially shrinking multipliers in the main block.
Exactly. It guarantees that at least a portion of the gradient signal passes straight through, undiminished. It's an express lane, ensuring a strong signal reaches the earlier layers, fighting the vanishing gradient problem architecturally.
Genius. No, ResNet uses addition, but there are other ways to do skip connections, right? Like DenseNet.
Yes, different strategies exist. ResNet's addition-based connection is efficient, but the input and output dimensions usually need to match. DenseNet uses concatenation.
How does that work?
In DenseNet, each layer receives the feature maps from all preceding layers. Concatenated together. It connects everything to everything going forward.
Wow, that sounds like massive feature reuse.
It promotes huge feature reuse, which would be very powerful. The downside, memory. Concatenating all those feature maps makes the network grow very wide, very quickly, demanding a lot more memory.
And there's also the UNet style connection that's more specialized.
Yeah, UNets are common in image segmentation, tasks where you need precise spatial localization. They have an encoder path that compresses the image down and a decoder path that expands it back up.
Okay.
The UNet skip connections bridge across from the encoder to the decoder at corresponding resolution levels. They feed the high-resolution feature maps from early in the encoder directly to the later stages of the decoder.
Why is that important?
It helps the decoder reconstruct fine-grained spatial details like sharp object boundaries that might have been lost during the compression phase. It preserves that high-resolution information.
Okay, so we have better components, we have these architectural highways. But the data flowing on these highways still needs managing, right? Keeping the signal stable during training.
Exactly. We need a kind of traffic controller for the data itself. And that brings us to normalization layers.
The big one there for a long time was batch normalization, or BN.
Right. BN was huge for convolutional neural networks especially.
How does it actually work? What's it doing inside the network?
For each mini batch of data passing through, batch norm calculates the mean and variance of the activations across that batch. It then normalizes the activations, subtracts the mean, divides by the standard deviation so they have roughly zero mean and unit variance.
Okay, standardizing the inputs to the next layer.
Exactly. And then, crucially, it applies a learned scaling, gamma, and shifting beta parameter. This allows the network to decide if the normalized state is actually optimal or if it needs to scale or shift it.
And the benefits. Why was this so impactful?
Well, the original theory was about reducing internal covariate shift, but the proven benefits are more practical. BN makes the optimization landscape much smoother.
Easier for the optimizer to navigate.
Much easier. It allows you to use significantly higher learning rates, which speeds up training dramatically. It also acts as a form of regularization, kind of like adding noise because the batch statistics fluctuate slightly, and it makes the network less sensitive to the initial weights. Faster convergence, more stable training. Huge win.
But then came transformers and large language models, and suddenly everyone's talking about layer normalization, LN. Why the switch? Why didn't BN work well there?
The core difference is what dimension you normalize over. Batch norm normalizes across the batch. It relies on having a reasonably large, stable batch to get meaningful statistics, mean and variance.
Okay. And layer norm?
Layer norm normalizes across the features within a single training example. It calculates the mean and variance using all the activations for just that one data point, ignoring the batch dimension entirely.
So it doesn't depend on the batch size at all.
Exactly. And that's critical for situations where batch statistics are unreliable. Think recurrent networks processing sequences of varying lengths. Or, crucially, transformers.
Why are transformers a problem for BN?
Often, due to the massive memory requirements of transformers, especially for long sequences, you're forced to train with very small batch sizes, sometimes a batch size of just 1 or 2.
And batch norm stats would be useless then.
Totally unstable and noisy. Layer norm, being independent of the batch size, works perfectly fine in these scenarios. Its stability made it the absolute standard for normalizing the inputs to the self-attention and feed-forward blocks inside transformers.
It's amazing how these different pieces fit together. It really drives home the point that it wasn't one magic bullet.
Absolutely not. The real success story here is the synergistic integration of all these techniques. Modern deep learning relies on combining them intelligently.
Can you give an example, like in a standard ResNet?
Sure. A typical ResNet family CNN combines, say, ReLU activations for stable nonlinearity, initialization for a good start, residual skip connections for that gradient highway, and identity mapping, and batch normalization after convolutional layers to stabilize the internal dynamics.
That combination lets them train reliably even when they're hundreds of layers deep.
Precisely. And then look at transformers.
Different combo.
Different but equally effective. They tend to use smoother activations like GELU or Swish. They absolutely rely on layer normalization because of the batch size issues, and they wrap both the self-attention and feed-forward modules within residual connections.
So it's this toolkit, smart components, Architectural highways and dynamic stabilization, like normalization. That's the recipe.
That multifaceted strategy is really the core principle behind designing deep networks that actually work today. We
Hmm.
effectively solved that fundamental crisis of gradient flow that held back the field for so long.
And the results are just everywhere. We went from maybe struggling with a dozen layers to routinely training models with billions, even trillions of parameters. It was a huge engineering effort against those vanishing and exploding signals.
And that victory, that ability to train truly deep networks, is what underpins almost all the exciting AI progress you hear about. It unlocked the potential that was always theoretically there.
It really is stunning when you think about the journey. So, a final thought for our listeners. If this combination, the ReLUs, the initializations, clipping the skip connections, the normalization, if that solved the fundamental barrier of depth and gradient flow,
Hmm.
what's the next barrier? What's the equally fundamental bottleneck we need to break through to get closer to, say, artificial general intelligence? What's the next seemingly impossible engineering challenge?
That is the multi-billion-dollar question everyone in the field is chasing right now.
That's definitely something to mull over. Keep that question in mind as you explore more AI concepts. This has been our deep dive into how we actually make deep learning learn.
Thanks for tuning in.
If you want to keep diving deeper into AI, definitely subscribe for more discussions like this. And if you're looking for more hands-on tutorials, practical guides on how to apply some of these ideas, check out the Ian Ochieng AI channel on YouTube. That's Ochieng. Lots of great stuff there. We'll catch you on the next deep dive.